Right, okay. Students, can you all hear me? Can you hear me, students? Right, okay. Right, okay. So, very good evening for all of you. So, students, last week we conducted our subject introductory session. So, today we are starting our first class. That means day one of atomic structure. So, last week I explained you what are the relevant things that you have to understand regarding the subject, right? So what are the things that we discussed in the last class? We discuss about what is chemistry and why you learn about this subject. uh, what are the applications, what are the career paths that you have to choose after doing chemistry. And I gave you what is the A level syllabus, and I gave you what is our A level paper structure, and what is our work plan, and what are the qualities that you should maintain. So when you are doing this subject, right? So I believe that you can understand those things that I explained for you. So keep those things in your mind. So from today onwards, we are going to start our workload, right? So the first thing is actually, can you please raise your hand? Those who received the tutorials, can you please raise your hand? Those who received the tutorials. What about the others? Right. Those who registered for the class, I have sent tutorials. Actually, the first batch of the tutorials, I've sent the first batch of the tutorials for students. So, yeah, you will get those tutorials very soon. Okay. And so for the second batch also, the tutorials will be sent. So don't worry. So today what we have to do is, so please take out your writing book if you don't have the tutorials, and write down everything with me that I'm going to discuss here. And when you get the tutorial, after you receive the tutorial, you can complete your model, right? Because we know that normally better we write down chemistry like subject everything in your writing book. So therefore, write down everything, and soon after when you get the tutorial, you can fill the tutorial, right? Okay, right, students. In our syllabus, what is the first unit? In our syllabus, our first unit that we have to start is atomic structure. So today we are going to start unit number one, atomic structure, right? Atomic structure. First of all, you have to know that what is the content. What are the topics that we have to discuss under this atomic structure unit? Okay. So I'm going to categorize the subtopics in this unit number one into 16 subtopics are there. So first of all, let's see what are the subtopics that we have to discuss under this atomic structure unit number one, right? So today we are going to start. The first topic is actually atomic theory, right? We are going to discuss about atomic theory. I'll explain that how this atomic theory is built. Today we are going to discuss about names of many scientists. Actually, we can say names of many philosophers, right? Who contributed the development of this atomic theory. So that is the first subtopic that we are going to discuss. And the second subtopic is actually we are going to discuss about a discovery of subatomic particles. Discovery of subatomic particles. Students, what are the subatomic particles that we have to discuss? What are the subatomic particles? We are going to discuss about three subatomic particles. There are more subatomic particles, but our concern is about electron, E minus 1, 0. I'll explain you what does mean by this minus 1 and 0 later. Try to understand this is the symbol of electron. And then we are going to discuss about proton. Proton is P11. And then we are going to discuss about neutron. Neutron means N01. So we are going to discuss these three subatomic particles, the story of electron, the story of proton, and the story of neutron separately under this topic, discovery of subatomic particles, right? So today we can start a discovery of electron, and I'm going to discuss about the cathode ray experiment today with you, right? Number 3. So the third one is actually atomic models. Remember, students, after discovering these three subatomic particles, they wanted to know how these subatomic particles are arranged inside an atom. Electrons, protons, neutrons, how these subatomic particles are arranged inside an atom. Then they develop some theories on atomic models. Understood? Ekan egollo atomic model ekak dunna. Egollo model ekak dunna atom ekata. Atom is look like this exactly. Electrons, protons, neutrons are gathered inside an atom in this way, right? For an example, the first atomic model that we are going to discuss in this lesson is Dalton's golf ball model. So there was a scientist, John Dalton. Actually, he was a school teacher and scientist as well. So he assumed that atom is look like a golf ball, right? It's very hard. We can't divide that one, right? Indivisible, right? We consider that is indivisible. We can't divide that one further. So John Dalton assumed that atom is look like a golf ball. Some says that billiard ball also. And the second atomic model that we are going to discuss is Thomson's plum pudding model. So Thomson assumed that atom is made of a sphere which is positively charged, and the negative charges are actually the electrons are dipped on, right, gather on that positively charged sphere. That is plum pudding model. And thirdly, we are going to discuss about Rutherford's nucleus model, right? There was a scientist known as Ernest Rutherford. Ernest Rutherford is the one who discovered the atomic nucleus. So that is known as nucleus model. Some says that a planetary model, like planets are orbiting the sun, these electrons are orbiting the atomic nucleus, right? So that is actually considered as the Rutherford's model, planetary model or the nucleus. And the next one is Bohr's energy level model. There was a scientist, Niels Bohr. So he represented an idea about how these electrons and everything are located inside an atom using the energy level model. So that is very, very important concept. Okay. So likewise, we are going to discuss about 4 main atomic models. Some of the models are very important. Now, recently I saw that my 26 batch students, they said that in the FWC paper, Fieldwork Center paper, made by Northern Province, they have given, in essay paper, they have given Rutherford's nucleus model. That means there is an experiment to discuss, which is known as gold foil experiment, students. Right? We are going to discuss that one, gold foil experiment. Ranpatra Pariksha. So, in that gold foil experiment, they have given a question from gold foil experiment. So normally they won't give these kind of questions, but see, the patterns are changing. So therefore, we have to learn everything properly. So atomic models is one of the very important subtopics that we have to discuss under the unit number 1. Right, let's see what is the fourth subtopic that we have to discuss. Atomic number, mass number. So quickly write down these things with me. If you have the tutorial, please complete the tutorial. Page number 1. Others, take out your writing book and write down everything with me. Okay. Atomic number. And then we are going to discuss about mass number. Right. And then we are going to discuss about isotopes. Right. So these are some basic concepts that we are going to discuss. Number 5, we are going to discuss about duality nature. Duality nature of electrons. I'll tell you what is this duality nature of electrons when we go for this topic. So just write down the topic here, duality nature of electrons. Number 6. Number 6 is very important, quantum theory. I'll explain you what is this quantum theory. So you don't have to be panic for this term quantum. Quantum means very simple thing. A basic fundamental particle in any system is known as quanta or quantum. So we are going to discuss about quantum theory in this topic. And I'll tell you that how this quantum theory related to the development of the theories in chemistry. Number 7, we are going to discuss about the location of an electron. So this is a very, very important topic. Location of electron. Number 8, we are going to discuss about electromagnetic radiations. Electromagnetic radiations. And I want to remind you that under this electromagnetic radiations topic, students, we are going to discuss some calculations, right? If you have gone through the tutorial that I have provided you, I have uploaded the PDF also. You can see that some of the calculations are there in the tutorial, right? Calculations are starting from the isotopes topic, right? In the examination, in the first term examination, you can expect calculation from isotopes. Then we have to go with the electromagnetic radiations. Very easy. These calculations are easy. So this is the topic 8, subtopic 8. So shall we move to the 9th one? I'm going to erase these things. So quickly write down everything. Quickly. Number 9. So the 9th subtopic that we are going to discuss is atomic spectra. Yes. Many students are saying that atomic spectrum is difficult to understand, but let's see in our class how I'm going to explain these things and how you are going to understand this one. Don't worry. Number 10, we are going to discuss about atomic hydrogen emission spectrum. Yes, this is the topic that they are asking. Frequently, they are asking questions in the exam, right? If they have given some questions from the unit number 1, most it can be from atomic hydrogen emission spectrum. I'll tell you what does mean by a spectrum, right? So don't worry about these terms. You are going to learn these things in this topic in upcoming sessions. Number 11. So what is the 11th subtopic that we have on? Sub-energy level concept. Sub-energy level concept. Right? Can you remember that I told you? So when you write down the sodium electron configuration 281, that was the electron configuration you learned in your O-level time. But now it's not the correct electron configuration. So we consider that the electrons are gathered, the electrons are filled to the energy levels. But we didn't discuss about any concept like sub-energy levels, right? So there are some sub-energy levels like S, P, D, F, and we are going to discuss about sub-energy level concept, sub-energy levels inside this topic, right? Number 11. Number 12. Number 12. So number 12 is atomic orbitals. Yes, atomic orbitals. This is also one of the very important topics, because under the atomic orbitals, we are going to discuss about 2 principles or 2 rules. One is known as Hund's rule, and the other one is known as Pauli's exclusion principle. Okay, so under the atomic orbitals, we are going to discuss about some important rules or some important principles that we can apply. Okay, number 13. So the 13th one is, students, we are going to discuss about electronic configuration. That means electron configuration, right? This is not the topic that you discuss in your O-level time. Huh? I told you that sodium, in O-level time, you learn that sodium is 281. But in A-level, we are writing the sodium's configuration as 1s2, 2s2, 2p6, 3s1. I'll teach you how we can write down these configurations correctly by applying the rules or the theories that we learn. Okay, don't worry. So these things are very easy. We are going to write down the electron configuration for first 56 elements in the periodic table. Hydrogen to barium. Hydrogen to barium. Number 14. So the 14th one is quantum numbers. Right? Earlier, I told you that there is a topic known as quantum theory. Now we have a topic quantum numbers. Many MCQs are there, past paper MCQs and school term test MCQs are also there. Most of the time they are giving questions from this quantum numbers topic as well, right? So therefore you have to learn it properly. Number 15. So number 15 is periodic table. Yeah. So periodic table, students, I'm going to draw the complete periodic table in this whiteboard, and you're also going to draw that one in your tutorial. So there are 118 elements in the periodic table, and we are going to we are going to know about those elements. There are 118, and we are going to write down the symbols. That's all. Okay. So we don't have any further discussion. So you have to know the periodic table. And one more thing I have to remind you that in the exam, they are giving a printed periodic table in your exam paper. So therefore, you don't have to memorize the complete periodic table. But at least you have to remember element number 1 to element number 56 in the periodic table. So we have a work plan to remember that one, especially when we write down the electron configuration from hydrogen to barium, 1 to 56, automatically you will remember the elements. So therefore, nothing to worry. So again, we are going to discuss about those elements under this periodic table, right? Number 16. So this is the last subtopic that we are going to discuss. So this is actually known as periodic trends. This is how they have given in your resource book, or else we can tell that these are atomic properties, right? Atomic properties. Students, some of the atomic properties you already learn in your O-level time. Do you know that? What are those atomic properties? So the first one is atomic radius. Atomic or ionic radius. Okay. Probably you have learned this topic in your O-level time. And then first ionization energy. First ionization energy. Can you remember the graph that they have given in your O-level time? We are going to learn that one again. Atomic co-ionic radius, first ionization energy. And the next one is electronegativity. Can you remember the Pauling scale? Don't worry, we are going to discuss everything again from the beginning. And the next one is electron gain energy. Electron gain energy. We are going to discuss about this topic as well. So under the periodic trends or atomic properties, we are going to discuss about these periodic trends. Atomic co-ionic radius, first ionization energy, electronegativity, electron gain energy. Students, this is the content, right? These are the subtopics that we have to discuss under the unit number 1, atomic structure. Today, we are going to start atomic theory, and then let's start to discuss about the subatomic particles, right? So did you write down these things quickly? Did you write down these things? Please raise your hand, those who wrote these things. Please raise your hand, those who wrote these things. Right. Now in the chemistry theory class, remember students, don't worry. I'm going to write on everything on whiteboard. So when you get the tutorial, you can complete the tutorial. Otherwise, if you wish that I want to write down, I have to take these notes in writing book again. Yes, right. So I appreciate that one. So therefore, you can take that notes in your writing book as well, but complete the tute as well. Okay. So quickly complete this one. Normally, when you are answering for the questions, use the chat box. And if you have any doubts, put your doubts in the chat box. Please use the chat box. Huh? Don't speak to the mic. Please mute your microphones throughout the class session. Yes, Rishma. Yes, what are the doubts you have? Anything? Please put your doubts in the chat box if you have any. Yeah, if you have space in the tute, students, if you have the spaces in the tute, please note down these things also. It's not compulsory, but I wanted to tell you what are the topics, and these are the things we have to discuss specifically under these topics, right? So it's not compulsory. Yeah, I already uploaded the soft copy. Okay, Gloria, I already uploaded the soft copy in the WhatsApp group. So please keep in touch with the WhatsApp group. Okay, always. That's very important. Please go to the WhatsApp group and check. Right. Okay. Now, second page of the tute. Again, I have given you a topic like what is chemistry. Okay, I explain you this one in the introduction session also. Therefore, I won't discuss that one here. So let's quickly go for the definition and quickly complete the note. What is the topic? What is the question they have given? What is chemistry? Now, all of you know what is chemistry, right? Because we learned that one in the last introduction session, isn't it? Write down in this way with me. The things in universe, the things in universe can be, the things in the universe can be classified, classified into two main, two main categories as matter and energy. Matter and energy. Please highlight the key terms, matter and energy. Please highlight the key terms, matter and energy. Matter is anything that, matter is anything that has mass, has mass and takes up space, takes up space while energy, while energy is ability to do a work, right? Energy is ability to do a work, ability to do work or cause change, cause change. Take the red color pen, students. Take the red color pen. Write down. Chemistry is the subject. Chemistry is the study of matter. Chemistry is study of matter and the energy, and the energy associated, associated with that matter. We had a discussion on this one, so I won't explain this one again. Please complete your note. Chemistry is the study of matter and the energy associated with that matter, associated with that matter. Please mute your microphones. Yes, we have a question in the chat box like this. So can we write down the definition of chemistry like this? Chemistry is the study of properties and behavior of matter. Yes. Yeah. But your definition is not completed, okay? Because you haven't mentioned anything related to the energy. So therefore, please include that one also. Okay. In the exam paper, they won't ask what is chemistry. Okay. So this is just an introduction. Okay. But you can write down your own definition. Doesn't matter. But give the idea that matter and energy relationship should be mentioned. Okay. Right. Okay. Now the next topic. So the next topic is the classification of matter, because mainly we are discussing about matter, right? Since we are discussing about matter, so let's go for the classification of matter. This classification is very familiar to you because this is the classification you learn in your O-level time, right? So let's see whether you can remember this one. So classification of matter, right? So when you consider matter, so this can be divided into two main parts, right? Matter can be classified into two main parts. What are they? So I'm going to first of all classify this one according to the physical nature, right? Depending on their physical behavior, look at this, according to the physical nature, according to physical nature, there are three types. Can anyone tell me what are those three types? You learn this one. Yes, we can say that solid, liquid, and gases, isn't it? Stress, this is what you learn, right? Solids, liquids, and gases. This is by depending on the physical nature. And we can categorize this one again by considering the chemical composition, the chemical nature, right? Let me write down here in this way. Look at this only. Matter again, in here we can classify it in this way, right? According to the chemical composition. According to chemical composition, we can categorize matter into two main parts. What are they? We can say that pure substances. And what is the next one? Pure substances, and in the next one, can anyone tell me? Mixtures. Yes, please recall your O-level knowledge. Pure substances and mixtures. And the pure substances again can be categorized into two main parts. What are they? Elements and compounds. Elements and compounds. So what are the examples for the elements? We can say that the examples for the elements, when you go for the element, students, we can say oxygen, nitrogen, hydrogen, helium, sodium, sulfur. So likewise, we can consider elements. Elemental form. And what are the compounds? Compounds means actually combination of few elements under a specific ratio. Water, H2O, ammonia, NH3, glucose, C6H12O6, sulfuric, H2SO4. So these are compounds. Can you understand? Yeah, carbon dioxide, calcium carbonate, right? Ferric oxide, hematite. So likewise, we can consider different elements are connecting together in a ratio, in a specific ratio to form compounds. So pure substances can be divided into two parts, elements and compounds. Got it? Right. Then students, tell me mixtures, right? Mixtures can be categorized into two main parts. What are they? Yes, very good, very good. Yes, Niyamai, very good. So the first one is homogeneous. Homogeneous. And the next one is heterogeneous. Homogeneous and heterogeneous. Can anyone explain me what is this homogeneous and heterogeneous? Right? What does mean by homogeneous mixtures and what does mean by heterogeneous mixtures? Can you tell me? Because homogeneous mixtures means everywhere in the solution, chemical composition is same. Chemical composition in everywhere of the solution is same. But when we go for the heterogeneous, remember the chemical composition is not same. Chemical composition means when you consider a particular volume of that sample, the things that containing in that particular sample, and when you take another sample, everywhere that amount of that particular substance is same. Now you just take atmosphere, right? You are taking one air sample from one particular area. Let's take area 1. For there, in there also, nitrogen percentage is 78. And you are taking another air sample from another area, that is area number 2. So there also nitrogen percentage is 78 as a volume fraction. So the composition is same. But in heterogeneous, we can't see that kind of a same chemical composition. We categorize them under the chemical composition. So these are pure substances, completely pure. And these are mixtures. So homogeneous means chemical composition is same. What are the examples? Let me give you some examples, then you can understand more. Let me consider here salt solution. We are taking salt and dissolving in water, preparing a solution. So salt solution is homogeneous. Likewise, when you take sugar and you are going to dissolve this one in hot water, then sugar's solution is also what? Homogeneous. Now, for an example, just imagine I'm going to mix here under the heterogeneous rice and sand, right? That combination is very bad, but I want to take this example because then only you can understand me. Heterogeneous rice and sand, right? So the chemical composition is not same everywhere. It can be different from one particular area to another. So therefore, this is what meant by homogeneous and heterogeneous. Got it? So matter can be divided into 3 parts according to the physical nature. One is solid, second one is liquid, third one is gases. And when it comes to the chemical composition, according to the chemical composition, pure substances and mixtures. Under the pure substances, we have 2 parts, elements and compounds. Elements means pure element. There are 118 elements in the periodic table, right? So these are one of them. And compounds, we know that these elements are combining together to produce these. Then students, let's go for the mixtures. Mixtures means they are not pure, right? So mixtures can be categorized again into 2 parts, homogeneous mixtures and heterogeneous. Homogeneous means, so for an example, we can consider salt solution, sugar solution. The chemical composition in everywhere in the solution is same. But when it goes for the, when we go for the heterogeneous mixtures, remember the chemical composition is not same everywhere. So that is completely different from one particular area to another area. So try to understand the difference between these two, right? Can you understand? So this is the classification of matter that you learn in your O-level time. Yeah, students, this is what we are going to discuss, right? Mainly when we go for these pure substances, in that elements, compounds, everything is made up of one particular thing, right? Matter is our topic. So then we are going to investigate matter. What are the particles? What is the fundamental particle of matter? And in that fundamental particle, what are the subatomic particles? How they discovered these subatomic particles and how these subatomic particles are arranged inside that. So this is our topic. Got it? So please raise your hand, those who understood the classification of matter. Quickly raise your hand. Quickly raise your hand, those who understood this one. Right. Okay, good. If you have any doubts, put your doubts in the chat box. Huh? Right. Now in the third page of the tutorial, I have given you small two diagrams like this. Okay. And below, I have given you that life is chemistry. Dilute your sorrow, evaporate your worries, filter your mistakes, boil your ego, you will get the crystals of happiness. So this is actually one of the quotes I got from the internet. So I think this will be very important for you as well. So this is a message for you. Try to understand what they are trying to say. Okay. So let's explore the world of chemistry. So here we are going to start from the first topic. Our first topic, subtopic of the lesson is atomic theory. The atomic theory of matter. The atomic theory of matter. Students, please raise your hand. Those who bought the resource book, or else at least you have the PDF with you now. Please raise your hand. So I bought the resource book, at least I have the PDF otherwise. Okay, very good. Okay. So when I'm teaching and when I'm giving the notes, when we explaining the theories, please have the resource book with you. Then you can study the resource book and you can compare resource book note and our note. And that will be very healthy for you, right? The atomic theory of matter, right? Now, I'm going to I'm going to tell you a long story. So that is a very ancient story. And here only we are going to discuss about few names as well, right? Now, students, we know that the universe is made by matter and energy. So the discussion of matter is known as chemistry. So ancient people, right? Ancient people. So they were very eager to find out how this matter is made. What is the fundamental particle? What is the basic particle inside this matter? Right? So there were so many philosophers, so many scientists, so many mathematicians, right? So there were so many intelligent people that they wanted to find out how this universe is made, the things in the universe is made, right? They tried to figure out what is the fundamental particle of matter, right? So the first idea of this fundamental particle of matter came from the Greek, philosophers, right? So today, the first name that we are going to learn here, look at this name, will you? Right? Right? So the first name that we are going to learn here today is Empedocles, right? Empedocles. Actually, he was a very ancient, a great Greek philosopher. So he gave an idea to the world that everything in this world, right? That means all matter is made up by 4 elements, right? So this is the basic idea that came to the world. The very first idea came by a philosopher, a Greek philosopher, who is known as Empedocles. Actually, he died by jumping to a volcano, right? Still, there is a volcano named as Empedocles in Sicily, right? So you can search those things in Google and YouTube and everywhere. So he was actually a great philosopher, right? Maybe his idea is wrong, but remember that is the start of everything. Students, I told you that now our discussion is about matter. So they wanted to know, they wanted eagerly to know how this matter is made. So he gave the first idea, an acceptable idea at that time, very ancient time. So he said that everything is made up by four elements. What are they? If you have the tutorial, you can see that one. So the last Airbender is also there in the tutorial. I have given you four diagrams, right? So the first idea came to the world by the Greek philosopher Empedocles. He gave an idea how this matter is made, the fundamental particles in the matter. He said all the matter is made up by four elements, just four elements. Now we are telling that there are 118 elements, right? So now we are in the now in present, right? So this is actually very ancient time. Okay? So at that time, so they believe that everything in the world is made by four things. One is earth. Earth means soil, earth. And the other one is water, right? And the other one is air and fire. Earth, water, air, and fire. So you have seen many movies, enemy movies, right? Cartoons, right? So the reason you know that last Airbender is also actually very famous, right? So in that film also we are talking about air, someone who can control air. So this is the first idea that came into the play about matter. Everything is made up by four elements: earth, water, air, and fire. This is the first idea came to the world. Can you understand? But later, remember this idea is actually faded. That means by the development of the science, by the development of the other science related fields, so they found that this is not the exact idea. This is very ancient, very common general idea, right? So yeah, as we see, if you consider the world, that means if you see the world, yeah, we also can see that everything is made up by these four. Earth is everywhere, water is everywhere, air is also everywhere, fire, yeah. So likewise, we can see that. But remember, by the development of the sciences, right, maths, right, kind of subjects, so they found that this world is made up, that means the matter is made up by a small particle, right? So the one who represented that idea is actually another Greek philosopher who is known as Democritus, right? So you have to write down the names correctly. Democritus. So Democritus said that matter, or else everything in the world, is made up by tiny, invisible, that means we can't see them, and indivisible. Indivisible means, students, we can't divide them further. Tiny, invisible, indivisible particles, right? So this was his idea. He's the person, he's the one who said that everything is made up by tiny, very, very small, invisible, indivisible particles, right? So in Greek, now in the Greek language, we say that something known as atomos. So this is actually a Greek term. This is the Greek term that we are using to tell that a tiny, invisible, indivisible particle. Later, this atomos Greek term converted into atom, right? Then now we are learning about atom, right? We are learning about atom. So we are learning about atom. This term, this word came from the Greek philosophers. Can you understand? So therefore, atomos is the correct term, students. That is the correct term. That is the Greek term that is converted into atom. Now we are using that one in English language, right? So who gave the first idea about the atom? Democritus. He said that the atom, the matter is made by tiny, invisible, indivisible particles, right? So I'll consider a small practical example like this, then you will understand this one more. So let's just imagine I'm going to take a piece of paper, right? Look at this one, Ilu. So I have a piece of paper. Look at this. Now just imagine this is the matter. And I'm going to tear this paper in this way, right? And I'm going to divide this one again. I'm going to tear another piece, right? And I'm going to tear another piece, right? That means I'm dividing this one further, right? Like this, like this, like this. I can tear another time, another time, another time. So likewise, I can tear this paper up to a small particle, right? So that is the idea gave by Democritus as well. Matter. So when you go inside, so we know how to zoom out, zoom in. So then when you go inside, we can see that the small particles. Take this a paper example. So this is the last remaining particle. Just imagine we can't see this one. Then indivisible, invisible, very tiny particle. So from these particles only that paper is made. So that is the idea given by Democritus. Can you understand? Right. Now, later, right? So later actually, so there were two prominent philosophers, right? There were two prominent philosophers. You have heard about the names of them. Actually, they are Plato and Aristotle. Plato and Aristotle. Plato and Aristotle. So Plato and Aristotle, they give completely opposite idea, right? Now, up to this level, that means up to this time, now Democritus said that the atom is made by tiny, invisible, indivisible particle. Then that's what human found about the matter up to that level, up to that time. But we know that Plato and Aristotle, they were very, very great philosophers, right? So in ancient time, they were very famous, they were very prominent, and they are so like legendary people, right? So they are very famous, right? So everyone is accepting what they say. Actually, Plato is the teacher of Aristotle. Aristotle is actually one of the students of Plato, right? So they said that there are no indivisible particles inside the matter. That means they are saying complete opposite idea about the completely opposite idea of what Democritus said. There are no such thing like indivisible particles, right? That means they could have said like, yeah, atom can continuously divide, right? Continuously we can divide. Now Democritus is saying that, so there is a tiny small particle which is invisible, indivisible. Plato and Aristotle, they gave an idea like there are no such thing like indivisible particles. So that is the idea given by Plato and Aristotle that you have to understand. So they are saying that no ultimately indivisible particles. Indivisible particles. Actually, now if you think with the modern science, this concept is somewhat correct, students. Now we learn that at the beginning we are learning the subatomic particles that we have inside an atom is electron, proton, neutron. Later, they found that other subatomic particles are there like quarks and everything. So it won't be limited, right? That means it's continuously going. That means we can't find out. Who knows? There can be another few subatomic particles that we don't know, right? So therefore, we can't talk about that indivisible particle. Maybe those subatomic particles again can be divisible. Then the idea given by Plato and Aristotle still somewhat valid in our modern science. We can't ignore those things. But remember, now we are accepting this one, right? That's why we are discussing about the next scientist actually is John Dalton, right? So John Dalton proved that yes, there is a particle. There is an indivisible particle. That particle is known as atom. So he said that the fundamental particle, particle inside matter is known as atom. Remember, students, he just didn't tell this one, right? So he had proof also. He had some assumptions. We are going to discuss about Dalton's atomic theory. Actually, mainly the main person that we are discussing in this topic is John Dalton, right? So he gave some ideas, he gave some assumptions on how this atomic theory, how this atom is look like, right? So from John Dalton's idea only, we are telling that I told you that golf ball model. Golf ball model means atom is look like a golf ball. You know that golf ball is very hard. We can't break that one. We can't divide that one. Indivisible. So this is the way that they developed the idea about the fundamental particle of matter. We know that the study of matter is known as chemistry. Then matter is made up of what? Empedocles, like philosophers, very ancient philosophers, they said that the matter is made up with 4 elements: earth, water, air, and fire. Then later, Democritus, like Greek philosophers, they told that yes, there is an indivisible particle which is very tiny, invisible, right? The Greek term that we are using to tell that invisible, indivisible, tiny particles are atomos. Atomos. That term converted into atom later. Then Plato, Aristotle, like very strong characters, very strong philosophers. So they gave their idea or notion that there are no indivisible particles in matter. Further, we can divide the particle. Further, we can divide the matter. Completely opposite idea about this. But later, John Dalton is actually, so he's actually a school teacher, British school teacher. And he was a scientist too. So he gave an idea with some proofs, some assumptions. Yes, the fundamental particles inside the matter is atom, right? It is known as atom, right? But now, students, we do not consider the fundamental particle inside the matter is not atom. So there are some other particles as well. That's why we discuss about the subatomic particles. So this is the history of the atomic theory that you have to know. They have clearly mentioned this one in your resource book. Remember these names, students. Sometimes in the first term test, they might ask, they might not ask, but you have to remember this history. That's very simple. Okay. So please note down these things quickly in your writing book. So if you have the tutorial, one more thing. Soon after the class, I will upload my handwritten tutor note is there. Handwritten note means the tute. I have filled the tute. So I will take some photos and I will convert that one into PDF and I will upload that one after every class. So then you can complete the note from there also. Okay. Right. Please raise your hand, those who understood the history of atomic theory. Please raise your hand, those who understood that one. Do you have any doubts? Yes. If you have any doubts, put your doubts in the chat box. Let's see. So what is the meaning of word ultimate? Ultimate means what? Ultimate means further, right? Ultimately indivisible, right? You can name ultimate level, right? Unlimited level, right? In that way. That means Plato and Aristotle told that the matter can be further divided, but the atom cannot be divided. Yeah, we know that atom, Plato and Aristotle told the matter can be further divided. Matter is made up with atoms. No? Matter is made up with atoms. So matter can be divided, and atom also can be divided. Okay, so that is the idea. Because the particle inside the matter is atom. If matter can be further divided, then atom also can be divided. So fundamental means basic particle, right? Basic particle. So that means the Democritus assumption is false statement. No. So Democritus idea is same. Students, you can see that Democritus, the idea given by Democritus and John Dalton, almost same, right? Democritus said that tiny invisible, indivisible particles are there. So John Dalton said that the fundamental particle, yes, as Democritus said, the fundamental particle inside the atom is what? Fundamental particle inside the matter is what? Atom. So here, the wrong idea is given by Plato and Aristotle. But we can't ignore these things also in the modern science. That's what I told you. So that is, you have to think about. Okay. Now, hereafter, all the theories build up with this John Dalton's idea. Atom there, inside the atom, what are the subatomic particles? And likewise, we have the further discussion. Understood? So, we are not accepting the idea given by Plato and Aristotle. But the idea given by them is sometimes valid in the modern science, right? Yeah, we can divide the particles. So the idea given by Plato and Aristotle is students, very simple, right? Listen to this one. Now, Democritus said that the matter is made up with tiny, indivisible particles. Okay, there are small particles inside the matter, right? So that particle cannot be divided further. But Plato and Aristotle, they are saying that no ultimately indivisible particles. So he is saying that there are no such particles, right? So he is saying that the particles can be divided, right? We can separate them into another few particles. Completely opposite idea given by Democritus. Understood? That's what you have to understand. No ultimately indivisible particles. Okay. So in the resource book, if you have the resource book, they have given a statement like later. However, Plato and Aristotle formulate the notion that there can be no ultimately indivisible particle. Right? There can be no ultimately indivisible particles. Right? So therefore, this atomic weave, that means this atomic theory given by Democritus, faded for many years. Then John Dalton, he proved that yes, there is a fundamental particle, basic particle that is known as atom. Right? Yeah. So the idea given by Plato and Aristotle, that is completely wrong. No, Plus, now this is the thing. You have to understand that in the A-level exam, they are giving only one MCQ question from this complete unit. Okay. Now, we can't ignore these things because we have to teach you these things because you have to know the history. But they are not asking questions from these things. Okay. Because I haven't seen any exam paper that they have asked what is the idea given by Plato, what is the idea given by Democritus, what is the idea given by Empedocles, right? But you have to know those things as a chemistry students. So that's why they have included these things into a resource book. And we are also teaching this one. You have to learn. Understood? So therefore, nothing to worry about these things. So now the first few lessons that we are going to learn in the classes is actually, try to learn what is chemistry exact. Okay. So I'm not going to give you some work yet because we are starting our memory booster program from May month onwards. So let's do some sessions, 3 sessions, 4 sessions. After that, let's go for the questions. Okay. So in the April month, take your time and explore these things, learn what is the beauty of this subject, what is exactly chemistry, those things. Understood? Now next week we have Single and Tamil also. So take a break, small break. Again, after that, we have to start our studies. Understood? So therefore, you just learn these things. So these are some kind of a history of the subject. Just know, okay? We can't sure that these things will give in the exam. Mostly they won't give, but even though they give these things, you should be able to answer these things because these things are very simple. Got it? Students, any doubts, any questions that you want to ask, please put your doubts in the chat box. So did you write down these things? Quickly write down. So I have explained these things in the tutorial by 5 points. So this is the summary. Okay. So therefore, write down this summary. Quickly. Okay. Right. Again, please raise your hand, those who understood everything that we discussed up to now. Please raise your hand quickly. Right. Now let's move to the next topic. Now, students, I told you that John Dalton, he said that the fundamental particle inside the matter is atom. Right. So our topic is atomic theory. So clearly we are discussing about the Dalton's atomic theory. Okay. So he made some assumption on the matter and the atom, the fundamental particle in atom, in the fundamental particle in the matter. So let's see what are the assumptions he made on this atom, right? Let's see. So you have to know about these things. These are few ideas that you have to understand, right? So we can say that Dalton's atomic theory, write with me, Dalton's atomic theory was based on four postulates. Four postulates. Right. So let's learn what are these postulates. Number one. First of all, write down these things with me and let's discuss these things one by one. First of all, write with me. Number one, look at this one. Elements are made out of extremely small indivisible particles called atoms. Yeah, that is the main idea. Okay, this is the idea given by Democritus as well. Elements are made out of extremely small indivisible particles called atoms. Now here the elements means, students, not that earth, fire, air and water. Elements means the everything, that means oxygen, nitrogen, helium, everything, that elements, the elements that they found. Right? Later they found the elements also. No? So those elements are made out of extremely small indivisible particles called atoms. That is the main idea. And we can understand that one easily. Now, what is the second theory behind on it? The second one. Right? So the second one is, look at this one. Huh? This is very important. All atoms of a given element, write with me. All atoms of a given element are identical in mass and size. In mass and size, but the atoms of one element are different from the atoms of all other elements. Yeah, this is actually very, very important idea given by John Dalton. Right? So this is very, very important idea given by John Dalton. Right. Students, let me explain this one by taking a small example like this. Now listen to this one very carefully. Yeah? Right. So what he is saying in his second postulate is, now just consider two elements like sodium and magnesium. Can anyone tell me which one has the highest mass, sodium or magnesium? When we consider the mass factor, which one is the highest? Yeah, magnesium, right? So magnesium has the greatest mass. So how do you know that one? Because students, magnesium is the element after sodium. Sodium's mass number is 23. Magnesium's mass number is 24. So you know that magnesium has the greatest mass compared to sodium, right? And the next factor I'm going to consider is size. So let me consider radius, magnesium, and sodium. Right. Let me see how many of you will answer for this question correctly. Can anyone tell me which one has the greatest radius? Magnesium or sodium? Yes. Very good. Right. Shabnam, yeah, your answer is correct. Right. Who has the greatest radius? It's not magnesium, students. It is sodium. So magnesium is coming after sodium, right? Then how? Yeah, magnesium is coming after sodium because of the number of protons and neutrons. Number of electrons are changing, right? So therefore, yeah, magnesium is coming after that. But it doesn't mean that magnesium should be the largest one than sodium. Can you remember under the atom, under the trends, periodic trends, we have a topic, subtopic known as atomic radius, ionic radius. So we have to discuss about the atomic radius. We are going to compare them. Plus, there is a rule, I'll teach you that one later. When you consider the period-wise elements from in one particular period, from left-hand side to right-hand side, the atomic radius decreases. That means sodium has the greatest radius. Understood? Even though that the number of electrons, right, number of protons are different, remember magnesium has the lowest radius. So sodium atom is look like this, magnesium atom is look like this. But remember which one has the greatest mass? Magnesium. So John Dalton said that when you consider two particular elements, sodium and magnesium, each and every, now you just consider sodium, will you? Each and every atom inside that element. Now I'm taking a sodium sample, students. I'm going to consider sodium sample. Each and every atom in that sodium sample has the equal mass and equal size. I'm going to consider another sodium atom, same size, same mass. I'm going to consider another sodium atom, same size, same mass. Then when you consider another different element, so it has same mass, same size in that particular element's atoms. Now these are magnesium atoms. Magnesium atoms are same, right? So when you consider different magnesium atoms, they are having equal sizes and masses. But when you consider magnesium atom and sodium atom, that means two different elements. So these are two different elements. So since they are two different elements, they have different masses, different size. But when you consider one particular element, atoms inside that element has equal masses and equal size. Can you understand the point? The second point is saying that all atoms of a given element are identical. Sodium atoms are identical. Magnesium, all the atoms are identical in mass and size. But the atoms of one element are different from the atoms of all other elements. Magnesium is not same as sodium. Magnesium is not same as sulfur. Magnesium is not same as chlorine. Magnesium is completely different from the atoms in other elements. Can you understand the idea? Right? Please raise your hand, those who understood that idea. Please raise your hand. And if you have any doubts, put your doubts in the chat box. I want to know it. So then isotopes have different masses. What about that? Yeah, that is isotopes, right? Isotopes have different masses when we consider number of neutrons. When we go for the isotopes, actually, this rule is the postulate that assumed by John Dalton is completely wrong. As you said, this idea is wrong. Remember, students, these are assumptions. Postulates means upakalpan, right? We are assuming. John Dalton assumed these things, right? We are proving that finally John Dalton is wrong. He said that the fundamental particle of atom is the fundamental particle inside matter is what? Atom, but it is not. There are subatomic particles also, later they found. So therefore, these ideas, first of all, so they gave ideas. Maybe these ideas are wrong, but these ideas will lead for the correct path of finding subatomic particles, atomic models, and everything. Understood? So this is the background. Okay. So this is the ground level. By depending on these things only, J.J. Thomson, Rutherford, so those kind of Chadwick, Eugene Goldstein, likewise scientists, they found the subatomic particles. After gave these ideas, they thought that, is this really correct? Right? So like you said, is that sodium, all the sodium atoms are having the same mass? Is that correct? So likewise, they found, remember students, not like us. So the ancient people, those philosophers had a lot of time to think. So philosophers means someone who is actually completely a free mind. That means he has the freedom to think, right? So that's how they gave the ideas. Now, whether that idea is correct or wrong, so that is another thing. That's a different thing. But remember, in general, by depending on these things only, all the theories are developed. Yes, but as you said, this idea is wrong when it comes to the isotopes. Okay, very good. Yes, that's a good question. Anything else? Any doubts? Quickly put your doubts in the chat box if you have any. Right. Now, number 3. Look at the third postulate given by John Dalton. Students, quickly write down these things. Please complete your note correctly. Note until you get the tutorial. So the third postulate represented by given by John Dalton was atoms are neither created nor destroyed in chemical reactions. So what is your opinion, students? Right? What is your opinion here? Atoms are neither created nor destroyed in chemical reactions. Yeah, that's correct. Now, for an example, so let me write down an equation like this, a simple equation that you know. Calcium carbonate is thermally decomposing into calcium oxide solid compound and carbon dioxide gas, CO2 gas. Got it? Calcium carbonate solid compound is thermally decomposing into calcium oxide and carbon dioxide. So you can see that all the elements are actually included in the right hand side as well. Calcium, calcium, oxygen, there are 3 oxygen, 1 carbon. Yeah, atoms are neither created nor destroyed in chemical reactions. That's correct. But remember, just imagine John Dalton didn't include chemical reactions without chemical reactions. Is that valid in the modern science? Now, I'm just telling you, right? Now, you and me, I'm telling you that, students, atoms are neither created nor destroyed. Is that correct? Let's see. So just think a little bit. No, that is not correct. Yes. Remember, ladies and gentlemen, that's not correct. If I say you that atoms are neither created nor destroyed, that statement is wrong. What about nuclear reactions? So when we consider the nuclear reactions, we know that matter is converted into energy. Gamma radiation, that radiation, so many radiations are there. And new elements are formed. We are discussing nuclear reactions in unit number 3, chemical calculations, at the end of the lesson. There I'm going to tell you that an element is completely converted into another new element. That means an atom is created. Another different atom is created. Another atom is destroyed. Right? Understood? So those things can happen in the nuclear reactions. But anyhow, at that time, now when we consider the time that these postulates represented, they haven't found anything related to the radiations, nuclear reactions. So in that level, atoms are neither created nor destroyed in chemical reactions. That's correct. All the time, that's correct. But if I say that atoms are neither created nor destroyed, only that particular phrase, that is wrong. Because in nuclear reactions, atoms can be destroyed or created. Sorry. Understood? So this is the third postulate given by JD, right? So JD means John Dalton, right? Number 4. Shall I erase this one? Shall I erase the second point? Do we need more time? Quickly. Okay, right. Usually in my online classes, students are using the chat box to say yes, no, done. Likewise. So I'm also encouraging you to chat with me in the chat box. Okay. Nothing to worry. So there are no big differences in our online classes and physical classes. So you can interact with me, even though I told you not to speak to the mic, but use the chat box. And so let's discuss what are the doubts we have. Okay. Right. So now fourth one. So in the fourth one, actually, he is talking about the compounds, right? Now look at this point. So this is also very important point. Look at this one. Look. Compounds are formed by union of two or more atoms, of different elements in a simple numerical ratio, right? Now look at this point. This is also very important. Compounds are formed by union of two or more atoms of different elements in a simple numerical ratio. Now look at this only. If I consider water molecule, H2O, hydrogen and oxygen, so they are different elements and they have combined together in order to form a compound. By using a simple numerical ratio, hydrogen to oxygen ratio is 2:1, right? So there are two hydrogens combined with one oxygen atom. So this is what John Dalton said. That's very simple idea, isn't it? Ammonia, NH3, right? Ammonia, NH3. In ammonia, NH3, you can see that nitrogen to hydrogen ratio is 1:3. So that ratio is 1:3. Got it? So compounds are formed by union of two or more atoms of different elements in a simple numerical ratio. That's correct. Right? That's perfectly okay, isn't it? So this is the fourth postulate. Okay. Right. Students, can you understand the four postulates that we discussed under the Dalton's atomic theory? And one more thing I want to tell you that along with these four postulates, he said that, can you remember that atomic model? What is the atomic model represented by John Dalton? What is he said? Dalton's golf ball model, right? John Dalton's golf ball model. He assumed that atoms look like a golf ball, right? Yeah. Compounds like oxygen, nitrogen from the same element So when you consider those things, the statement is violating. But general idea means compound means what he trying to say is compounds formed by the different elements. Okay. But as you said, I know that you will ask this question. So oxygen, nitrogen, hydrogen. So when we consider those kind of things, those kind of polyatomic compounds, right, from the same element, so then we can consider this statement is violated. But general idea is okay. Okay. Yeah. There are so many compounds with no simple numerical ratio. Okay. So there are so many compounds with very large values. But here we know that is giving an idea about simple molecules like these things: ammonia, water, carbon dioxide, those kind of things. So I told you, again, I'm telling you that these points, these postulates, these assumptions are not 100% accurate. I told you that these are few assumptions, may be correct. Sometimes they are partially correct. Sometimes they are completely wrong. Sometimes they are completely understood. So these are few assumptions. Take the general idea. Understood? Simple numerical ratio also. So that is also an issue. Yeah. So complex molecules like hemoglobin, right? So we know that soap, chemical formula of soap. So there are so many fatty acids are there. So in those compounds, we don't have any simple numerical ratio, right? Large numbers are there. So in sucrose also, we know that there are so many carbon, hydrogen, oxygen atoms. So therefore, this statement is not completely correct. So, but try to get the idea, okay? General idea, what he is trying to say. Anyhow, these things are actually wrong. In the modern science, that is wrong. Okay? Now, we are not currently accepting Dalton's atomic model. No. Still, are we telling that the atom is made by kind of a golf ball? No, right? Because we know that there are subatomic particles as well. These are assumptions. Understood? Okay, in the tutorial, I have given you a picture of this scientist, John Dalton. Please have a look on him. Right. Now, let's quickly revise what we learned up to now. Okay. So today we started with the content of our first unit, atomic structure. Then I gave you the definition for the chemistry, and we learned the classification of matter. Please revise what we learned today. And then we discuss about the atomic theory and the history of the atomic theory. And there I mentioned here few names to remember. One is Empedocles, and we know that he's the one who gave a basic idea about how the matter is made. Right? He said all the matter, everything is made up by four elements: earth, water, air, and fire. Then a Greek philosopher, Democritus, he gave an idea like matter is made by tiny, invisible, indivisible particles. Later, those particles were known as atomos, the Greek term atomos, converted into atom. Then, after a few years, actually, Plato, Aristotle, like very strong characters, very strong philosophers, they gave the completely opposite idea given by Democritus, and they told that no indivisible particles inside the matter, so we can divide them further. Completely opposite idea given by Democritus. right? So therefore atomism, right? Atomism faded for many years, and later again, scientist and teacher John Dalton, he gave an idea about this atomic theory again. Atom. What is an atom? Right? That is the fundamental particle inside the matter. And he assumed that atom is look like a golf ball. And by depending on that golf ball model, he gave four postulates, four assumptions. Those are not perfectly correct. Those are assumptions. The first thing is actually, as we know, the fundamental particle, he named that one as atom inside the atom. And then he told that, what is the second idea he gave? So the second idea that he gave was, when we consider one particular element, the atoms inside that element are equal in size and mass. But when we consider two different elements and they are atoms, so they are completely different from size as well as mass. And the third point we learned today, atoms are neither created nor destroyed in chemical reactions. And the fourth one, compounds are formed by union of two or more atoms of different elements in simple numerical ratio. And final thing I want to remind you, maybe these postulates are correct, wrong, maybe these are partially correct. So have that in your mind. Right. Then this is what you have to learn about atomic theory. So everything that we discuss is given in your resource book also. So you can read that one and try to get the idea. And one more thing, I'm suggesting you to search in YouTube, search in Google. So what is the history of atomic theory? You can gain many knowledge from YouTube and Google as well. So you can read the books also there. So many e-books are there. Read them and try to collect some knowledge about atomic theory, right? So since you have time now, you can read those things, because after we discuss about these things, from the next month onwards, from the May month onwards, we don't have time to look at these things. Now these things are becoming very easy things when you go for the next chapters. Okay, then with that atomic theory is over, please raise your hand, those who understood the concepts of the atomic theories we learned today. Do you have any doubts? If you have any doubts, please put your doubts in the chat box quickly. No doubts. Good. Right. Then, students, let's go for the subatomic particles. Yes. Right. Now, they were thinking that the fundamental particle in matter is atom. Now, we are going to prove that John Dalton is wrong. See, he gave many things, right? He gave many ideas, but finally, right, present proves that history is wrong, right? Interesting, isn't it? So what happened was actually they conducted few experiments. Now discovery of electron is actually, it was an accident, students. They didn't find out the electron intentionally. Write down the topic. If you have the tude, go to the page number 5. So the topic is actually discovery of electron. Okay, discovery of electron. That is our topic today. Now what happened was, so there are so many scientists actually at that time, 18s, in 19s, they conducted many experiments on many scientific things, right? So there was a scientist known as Michael Faraday, right? So he conducted many experiments on electricity. We are discussing about Faraday laws in unit number 13, electrochemistry. There are 2 Faraday laws, okay? But he also, we have to remind him because he's also one of the reason that we found the electron in chemistry. Okay, so I'm going to discuss two stories, and finally we come to one particular point, right? So therefore, listen for this one very carefully. Now, Michael Faraday and some of the scientists were conducting some experiments on passing current electricity through the physical mediums like solid, liquid, and gases. Okay, so they tried to pass the current electricity through the solid medium. Just take a copper wire. So through a copper wire, so if it is a conductive one, we know that the current electricity can be passed. So they succeeded in that. That means solid, the physical nature solid can pass the current electricity. And the liquid state. Yeah, the liquid state also possible. They found that in the liquid state also current electricity can be passed. So the nice example is electrolytic cells, electrochemical cells. You know that we are using a liquid medium, aqueous medium. So they succeeded in that. But Michael Faraday couldn't find out whether the gaseous medium, whether gas medium, gases can pass the current electricity, right? But after him, many scientists tried to find out whether this gas medium pass the current electricity. Try to understand what I'm saying, right? This is the story of the electron. This is how they started. No? So this is actually something on electricity, right? They conducted a small experiment on electricity. Finally, they found a particle. They found a particle like electron. First of all, those particles were known as cathode ray particles. I'll tell you, right? So, so they tried to pass the current electricity through the gas medium. So for that one specifically, they built an equipment or experimental setup which is known as cathode ray tube, or else this is known as Crookes tube, right? So there were many scientists actually conducted experiment on passing current electricity through gas medium. One is J.J. Thomson, right? Look at the name J.J. Thomson. Have you heard about the name J.J. Thomson before? Tell me, students, what is the contribution by J.J. Thomson to the chemistry, development of the theories in chemistry? What is the contribution by J.J.? Huh? Can you tell me, please? Yeah, he's the one who found the electron. Understood? So we are giving the honor to him, the one who found the electron, right? But remember, so he can't take the 100% honor. Understood? William Crookes, Julius Plucker, Wilhelm Hittorf, J.J. Thomson. So these kind of scientists, bunch of scientists, they conducted experiments on passing current electricity through the gas medium, right? Actually, they succeeded in that particular experiment. Okay, but the issue is something happened accidentally that they never expect. ඒගොල්ලෝ හිතුවේ නෑ එහෙම දෙයක් වෙයි කියලා. Right? They never expected that kind of a thing. So let's see what is that unexpected scenario happened in that experiment. Okay, right. Now, in the tutorial, I have given you that in the page number 5. I'll read those things, so you don't have to write down those things. If something is there to write, I will tell you what are the things you have to write, okay? Discovery of electron. However, the scientists discovered later that electron, proton, neutron are the main fundamental particles in matter. So let's write down that one as a point. Later, found that there are 3 fundamental particles inside matter, inside the matter, inside the atom. So who are they? What are they? Electron, proton, neutron. Okay, electron, proton, and neutron. Electricity was sent and tested in all three states, solid, liquid, gases of matter, to analyze conductivity. The scientists, including Michael Faraday, right? So let's write down this point because this is important. So let's write down this point. If you have the tute, you don't have to write down, but others, please write down these things with me. The scientist, including Michael Faraday, please highlight the name Michael Faraday, right? Who sent electricity through liquid? Who sent electricity? Who sent electricity through liquid? Through liquid. Discovered that there was a fundamental particle in electricity. Remember, students, in electricity, okay? But our topic is matter. Electricity is energy, right? So I told you that we are going from two different paths and coming to one particular point, okay? One path. We are discussing about energy. We are discussing about matter. Michael Faraday found that fundamental particle in energy, especially electricity, is also electron. But our topic is, what is the fundamental particle in matter? John Dalton said that is atom, but there are three subatomic particles, electron, proton, neutron. So already Michael Faraday conducted few experiments by passing current electricity through liquid medium. He discovered that there was a fundamental particle in electricity, right? Later, a scientist who is known as Johnston G. Stoney, right? Students, you have to remember these names, okay? You have to remember these names. Johnston G. Stoney, right? Johnston G. Stoney named it as electron. But remember, this is not the discovery of electron. So what are you trying to say? Now, just now in this paragraph, you have mentioned Michael Faraday conducted an experiment, discovered that the fundamental particle in electricity is electron. Johnston G. Stoney named that one as electron. Yes. But students, this is on electricity. Electricity is not matter. Our topic is matter, right? What is the subatomic particle inside the matter which is negatively charged? Electron, that electron. I'm talking about that electron inside the matter. Understood? I'm talking about that. I'm not talking about the electron they found in the electricity. Same thing, right? But they discovered in two different ways, right? We are going in two different paths and coming into one point. Michael Faraday conducted some experiment using energy and they found fundamental particle in electricity is electron. Now, J.J. Thomson, Julius Plucker, Wilhelm Hittorf, William Crookes, they conducted few experiments, and using those experiments, they found that something known as cathode ray particles, later cathode ray particles identified as electrons. We are going through that story. Again, apita may story ka adala naha. Understood? We are coming to the same point, electron. But we are not discussing about this story. Make අපිට අදාළ නැහැ. Right? This is not relevant to us. So the story that we have to discuss is about the fundamental particle inside an atom, which is electron, under the topic matter. Right? So try to understand difference between these two. Okay? So that means according to this part, according to this thing, actually we have to tell that the electron was found by Michael Faraday, right? No, I told you. So this is a different story. We are talking about the fundamental particle in matter, not the energy. Who found the fundamental particle electron in matter? J.J. Thomson. The one who named the electron is always the one person, James Johnston G. Stone. Right. So then, can you tell us the story behind how they found the electron using this matter, concept matter? Yes. That's what we are going to learn. Right. In the tutorial, I have given you two images of Michael Faraday and Johnston G. Stoney. Remember, Michael Faraday is the one who conducted experiments on electricity, especially passed the current electricity through the liquid medium, discovered that the fundamental particle in electricity is electron. The one who named the electron is Johnston G. Stoney. Please remember these two names, and they are okay. Right. Now, now look at this one. Okay. Now let's come to our topic. How they discovered this electron inside matter. Right. Now, Michael Faraday couldn't conduct an experiment properly to pass the current electricity through the gas medium. But some of the scientists were there, they tried.
Sir, cannot hear you.
Okay, can you hear me, students? How about now? Now, can you write? Now, listen to this one, okay? Listen to this one very carefully. Now, what I was talking about here. Now, I'm going to connect this one to a very important topic. So, therefore, listen to this one very carefully, more than before, right? So, I'm going to discuss cathode ray tube here. Okay, you will do this experiment in your school. So, therefore, let's see what is that experiment. Okay, right. So, these scientists, this bunch of scientists, they try to pass the current electricity through the gas medium. And let's see what happened exactly. Okay. Right. Right on the next point. So the next point is here they have used an experimental setup for this one. Setup for this known as discharge tube. Okay, this is known as discharge tube, which was invented by whom? Sir William Crookes. Sir William Crookes. Sir William Crookes. And it is also known as, and it is also known as, and it is also known as what? Remember, it is known as Crookes tube, or else it is known as cathode ray tube. Cathode ray tube. Okay. Let's see now how this cathode ray tube is working and how this experiment is conducted using this Crookes tube or cathode ray tube. First of all, write down these 2 points quick. I'm going to explain you the experiment. Wait. Done. Right. Now look at this one, okay? So let's see what is the experiment they conducted on passing current electricity through gas medium. So the experimental setup they used is known as Crookes tube or else discharge tube, or else we can say cathode ray tube. Okay. So our next topic is cathode ray tube, Crookes tube, or else discharge tube. You have to name these. You have to remember these names. Okay. That's why I'm giving all 3 names here. Please remember these names. Right. Now look at this one. So this is the experimental setup of cathode ray tube, which was invented by Sir William Crookes. What he has done is this kind of a hard glass tube is taken. It's very hard, okay? It's very hard. And 2 metal rods were connected for both the sides of the glass tube. And thereafter, these 2 metal rods are connected to a high voltage source. High voltage source. just imagine this voltage source. The voltage value is more than 10 kilovolts, right? This is more than 10 kilovolts, okay? High voltage source connected to a high voltage source. In this way. Students, just imagine this is the negative terminal, right? That means the negative terminal of the voltage source is connected to this one. And the positive terminal of the voltage source is connected to this one, right side. Therefore, this is known as cathode. Okay, so the negatively charged one is known as cathode. And the positively charged one is known as anode. Cathode and the anode. Got it? And in order to maintain the pressure inside the glass tube, they used here a vacuum pipe. Okay? They used vacuum pipe here to maintain the pressure. Okay, I'll tell you, we are using vacuum to reduce the pressure, right? You can, I'll tell you what is the pressure value they maintain inside this tube. So this is vacuum pipe, right? And do you know what happened exactly? Remember, students, they discovered that some of the radiations are emitted from the cathode side to anode side. From the cathode direction to anode direction, they discovered that some of the radiations or particles are moving in this way. Exactly, they are starting from the cathode, right? Remember, exactly, they were started from the cathode in this way. And they are moving towards the anode. Started from the cathode and they are moving towards the anode in this way. Remember, students, since they are started from the cathode, they are known as cathode rays. What are they? They are known as cathode rays since they started from the cathode direction. Exactly from the cathode. Right? Remember, these radiations are not visible for our naked eye. Right? So, what they use is actually they used a fluorescence screen. A fluorescence screen means, students, a screen which is sensitive for radiations. We can observe radiations. That means when the radiations are falling to that screen is starting to glow. So what happened was actually they use a screen behind this cathode ray tube, and addition to that one, right? Addition to that, they coated a compound which is known as zinc sulfide. Okay. The reason that they coated zinc sulfide in the anode direction, okay, this is anode direction, because in the anode direction we can clearly observe that these radiations are coming and colliding with the wall of the glass tube. So this is actually considered as zinc sulfide. Zinc sulfide coated fluorescence screen. Fluorescence screens are used to see the radiations. Okay. The reason I use the green color is exactly we can see them in the green color, students. Exactly, they were seen in green color. Understood? So that means the radiations are emitted from the cathode is green color, right? No. Don't misunderstand that one. Every year we are telling that for the students. Students, cathode rays are not green color. Because of the fluorescence screen that we use, we can see the cathode rays in green color. Because we are using the fluorescence screen to see the cathode rays. It doesn't mean that cathode rays are green color. Okay, understood? So we can observe the rays in, right? One more thing I want to tell you that Do you know what is the pressure they maintain inside the glass tube? So the pressure that maintained in the glass tube was 1/100 mercury millimeter. Very, very low pressure. Very low pressure. So that's why they used vacuum pipe. And remember, students, they use helium like a noble gas, very light noble gas, helium. The reason that they use helium inside the glass tube is helium is not reacting with the others. Helium is an inert gas. No, we know about it. So therefore, they are not reacting with the others. Okay, actually, we are removing all the air inside this glass using the vacuum pipe. So you can see, understand that the pressure is this one. And then they inserted helium gas. Right? Then this is connected to high voltage source, which is greater than 10 kilovolts, sometimes very close to 20 kilovolts. Right? Very high voltage source. Okay. Then they observed that from the cathode direction to anode direction, some of the radiations are emitted. Those radiations can be seen, right? They saw these radiations through a fluorescent screen, right? And from the anode direction also, they quoted zinc sulfide. Zinc sulfide is actually white color quote. So using zinc sulfide fluorescent screen, they observed that radiations are coming in. Right? These are exactly green color. Right? These are green color because of the fluorescent screen. Right? It doesn't mean that cathode rays are green color. Okay. Right. Now remember, students, this is actually not expected. This is not expected. Now J.J. Thomson was very curious. He was very curious to find what are these radiations exactly. Using this experiment, actually they got two productive results. Number one, they proved that gases can pass the current electricity, right? You can see that the radiations are moving here. That means electrical spark is there. So therefore, gases can pass the current electricity. And the second thing, when they keep that fluorescent screen, they can see the green color. That means radiations are emitting. What are these radiations? They wanted to find out what are these radiations? What are these particles? J.J. Thomson was very eager to find out what are these things. What are these radiations? He conducted three main experiments. That is what now we are going to learn next. Using these three experiments, he concluded that these particles are what? These particles, that cathode rays are none other than what? None other than cathode rays are none other than, yes, complete it. So you can do it. Cathode rays are none other than electrons. They were electrons. This is the story behind the discovering electrons. Now you should be able to explain this experiment to anyone. Okay, now you know the story, right? Okay, first of all, I'll show you a small video clip. So have a look on this.
Cathode rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to the negative terminal of the battery, and the anode of the tube is connected to the positive terminal of the battery. It was observed that, at normal pressure, the gas did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 millimeter Hg, and
can you see the screen? Can you see the video properly? Can you see the video properly? No. Give me a minute.
Cathode rays are
How
produced
about
in a
now? Can you
discharge
see the
tube.
screen?
A
Can you see the
vacuum
video?
pump is used to evacuate the discharge tube.
Yes. Good.
The cathode of the tube
Have a look
is connected
on
to
this
the
video.
negative terminal of the battery, and the anode of the tube is
This
connected
is
to
the
the
cathode ray.
positive terminal of
Look
the
at the cathode
battery.
and the anode.
It
Vacuum
was
pipe is
observed
there.
that, at normal
Connected to
pressure,
high
the
voltage
gas
source.
did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 millimeter Hg, and a high potential difference between 10 kV and 20 kV was applied, at the end of the tube, a glow was seen on the walls of glass tube. The rays emitted by the cathode travel towards anode. The attraction of rays towards anode reveals that the rays carry negative charge. Properties of cathode rays are: 1. When any object is placed in the path of the cathode rays, these rays cast shadows. This shows that cathode rays travel in straight line. 2. When a wheel was placed in the path of cathode rays, the wheel rotates. This shows that rays consist of some particle and some kinetic energy. 3. In the presence of an electric field, the rays are deflected towards the positive plate. This confirms that cathode rays consist of negatively charged particles. 4. In the presence of a magnetic field, the rays are deflected. This shows that the cathode rays are affected by the magnetic field.
Right. Now in that video, you saw that how the cathode ray tube is made, as I explained you. So in that video, they explained some experiment conducted to find out the properties of these cathode rays. For an example, they used electric field and to see the deflection of the cathode rays, and they used magnetic field to observe the deflection of cathode rays, and they used something like some kind of a metal plate, and it is started to rotate towards the anode. Right. So I'm going to discuss those experiments. Those are the experiments conducted by J.J. Thomson to find out the properties of the cathode rays. Because at the beginning, they didn't know these are electrons. So they wanted to find out what kind of radiations are they. Right. So using those experiments, they had a conclusion. They came for a conclusion by, yes, these are electrons. Okay. Right. Now, first of all, if you have the tube, in the page number 6, under the cathode ray tube, you can draw this one. Others, please take your writing book and quickly draw this one. Please draw this one quickly. Students, I would be very glad if you can do this one for me. Soon after the today's class, now this is the day that you learn theories from me, right? So soon after the class, please put a small feedback about our first day, the first day experience in our class, to the WhatsApp group. Okay, so directly to the WhatsApp group, I want to see. So whether it is a good or bad, doesn't matter. A feedback about the first day in the class. Okay, so after the class, please send me a small message, a feedback about the class. Okay. quickly draw this one. And I'm going to ask you two questions using this diagram. You have to answer for those two questions. Some general knowledge questions. Okay. What is the reason for coating zinc sulfide? Yes. The reason for coating zinc sulfide is now they wanted to see these radiations, right? So they knew that some of the radiations are emitting. They wanted to see those radiations. So when you coat the zinc sulfide, so zinc sulfide is actually a fluorescent compound. That means zinc sulfide compound is sensitive for the radiations. Right? When the radiations are coming towards the zinc sulfide, when they are colliding with the zinc sulfide coat, the zinc sulfide coat is glowing. Dilisenda padanga. Polapata dilisenda padanga. Then we can identify the radiation spots. Radiations. That's why they coat zinc sulfide. And the next thing is, in order to analyze the path, what they will do is, they will do same thing. They will keep a fluorescent screen, a large one, behind the cathode ray tube. Then you can nicely see that radiations are moving from here to here. In order to see that the radiation spots, you can see those things using this zinc sulfide coat, which is applied behind the amp. Right, okay. Now students, I told you that I'm going to ask you two questions. So I want you to answer this one very carefully. Yeah? My first question is, why they maintain a low pressure? Anyone, please? Can anyone answer for this one? Why they maintain this kind of a low pressure? Reason. What is the reason behind it? As in, for the passage of current. For the passage of current. No. That's a good try. To observe the cathode rays. Yes, Akash, yeah. To not the tube shatter apart. Yes, very good. That is the reason. That is the reason. Remember, students, if we maintain very high pressure inside the glass tube, this glass tube can be broken into parts. Right? Boom. So therefore, we can't maintain high pressure inside the glass tube. Remember that one. When the pressure is high, this glass can be broken. Okay, so that is the reason we are using a low pressure. And the second one is why we are using very high voltage source. What is the reason behind that? So they could have used a very small voltage here. What is the reason behind that? First, they conducted the experiment to pass the current electricity through the gas medium. First, this is not the solid or liquid. In order to pass the current electricity through the gas medium, definitely we have to give a high voltage source. And we have to form some radiations. You know that these radiations are going with. So this is actually a continuous flow. Right? In order to have this kind of continuous flow with the same speed, definitely we have to give very high voltage source. Otherwise, just imagine you are using very small voltage, then the radiations, not radiations, actually the experiment is completely unsuccessful. Then there won't be any current passing through the gas medium if we don't give this kind of a high voltage. So that's why, that is the reason we have to give high voltage. To pass this current through the gas medium properly with the constant acceleration. That is the reason. Okay. Try to understand. Since we are applying high voltage, we can't apply high pressure. We have to reduce the pressure. That's why they have connected vacuum pump and reduce the pressure first of all, and they have included the one of the lightest gases. First one is hydrogen and the second one is helium inside it. Okay, I'll tell you a very interesting thing. Now this is the discovery of electron, right? The discovery of proton, the positive particle is also happened in the same tube, same experiment. Behind the cathode, they observed that a red color glow, question mark. So that is actually going to learn in the next class, right? So that is, I raised the curiosity. Now you have to find it before you come to the next class. We are going to discuss about a red color glow behind the cathode, right? Cathode rays means the green color glow behind the anode. So that's what we are discussing, cathode rays. So proton, discovery of proton means green color glow behind the, right? So you have to know how those things are, how those green color glow and the red color glow is made. Okay. Yeah, one of the doubts. No, not anode. Anode is not red color, students. It doesn't mean that anode is green color, cathode is red color. It's not like that. Those radiations are glowing because of the fluorescence screen in that particular color. Understood? And now, you may have a question like, sir, then radiations are colorful, right? No, radiations are not colorful. Okay. So remember that neither cathode nor anode, no radiations colorful. Okay. So keep that in your mind. So nothing is colorful. Because of that fluorescence screen only, we can observe those things in colors. Okay. Right. Okay. Shall we have a note quickly? So can't we say like this, the usage of lowest pressure is to observe the current conducts in the lowest pressure, because in the atmosphere pressure, gases cannot conduct electricity. Yeah, that is also a good point. Yes. Yeah, we can accept that one. No? So look at this one. Abia Fahar. So can't we say like the usage of lowest pressure is to observe the current conducts the lowest pressure, because in the atmosphere pressure, gas cannot conduct electricity. Yeah, that's also correct. Now, in the normal atmosphere, we know that gases is not, the current electricity is not passed, right? In the normal atmosphere. So, do you feel that sparking the current? No, in the atmosphere. No, right? So, therefore, one of the reason, easily current can be passed through a low pressure medium. That's correct. So, that is also one of the reasons. Yes, very good. That's a good reason. Right. So if you have note down this one, shall we move to the note? Please raise your hand, those who note down this cathode ray tube. Do you need more time for this? No, right? Okay. Then let's move to the page number 7 in the tube. And others, please take the note in your writing book. No, cathode means negatively charged one, negatively charged metal electrode, and anode means positively charged metal electrode. Understood? Right with me, it was difficult to send. It was difficult to send current electricity through the air, through the air. Therefore, two metal electrodes two metal electrodes were used in the presence of helium-like gas. We can't remove the complete all the gases in the all the air in the glass tube, because we are conducting experiment to check whether the current electricity pass through the gas medium. So definitely we have to use a gas. So here we have used helium like gas at very low pressure. It is about 1/100 mercury millimeter. Some says that 1/1000, 1/10,000, likewise, very low pressure values. Yeah, starting from 1/1000, 1/100 mercury millimeter, hard in a hard glass tube. In a hard glass tube. These two electrodes were connected. These two electrodes were connected to a high voltage source. To a high voltage source. It is about 10 kilovolts. 10 kilovolts. Then cathode produced a stream of invisible radiations. Yeah, I told you that we can't see those radiations for our naked eye. Then the cathode produces a stream of invisible radiation. That's why we are using a fluorescent screen, a sensitive screen where we can use to see the radiations. Although the rays could not be seen, their presence was detected by zinc sulfide coated fluorescent screen at anode side. Okay. Last point. These rays are called cathode rays. Cathode rays, as starting from the cathode. Please highlight the last statement. These rays are called cathode rays as they're starting from the cathode. That's why they are known as cathode rays. Understood? Yeah, don't worry. I'm sharing the recording with you. Don't worry. Right. Okay, students, are we done? Did you write down these things quickly? Done. Good. Right. Okay. Then what next? I told you that J.J. Thomson was very eager to find out what are these radiations. Exactly what are these particles or radiations. So he conducted several experiments to find out what kind of radiations are these. So we are going to discuss about three main experiments conducted by JJT. JJT means J.J. Thomson. And let's see what is the experiment and the observation and what is the conclusion that he obtained from that particular experiment, right? Let's see. So the very first experiment he conducted was he used an electric field to discover the deflection of cathode ray stream in the presence of that electric field, right? Let me draw the diagram and show you that, right? Experiment number one conducted by J.J. Thomson, right? So this diagram is very important, okay? Look at this only, look. Now this is the cathode ray tube. So now here we have the cathode. Students, in this diagram, actually, we are using anode very close to the cathode. Here we are using a perforated anode. Perforated anode means, so there is a hole, right? There is a hole at the middle of the anode. So just imagine this is a circular metal plate, right? So there is a hole. So that's how, this is the way that I can draw this one. So this is a cross-sectional diagram, right? In this way. Right. So as usual, these two were connected to a voltage source and pressure, gas, everything are same, right? It changes. The position of the anode is a little bit different here. So now this is the cathode and this is the anode. Cathode, right? And this is the cathode and the anode, right? Now what he has done here, he used positively charged two metal plates in this way. He kept two charge plates in the path of the cathode rays, right? Just imagine this is the positively charged metal plate and this is the negatively charged metal plate. That means indirectly what he has done, he has created an electric field in the path of the cathode rays, right? So I can say that this is actually charged. These are charged electrodes or metal plates, charged electrodes, right? So the intention was actually to create an electric field, positive and negative. And remember, students, what happened? Now, from the cathode to anode, we know that cathode rays are emitting. Cathode rays are moving in this way. Like this, cathode rays are coming. Right? Now, this is the path of the cathode rays. Look at this one. Right. Okay. I have a question for you. Now, you just imagine you are J.J. Thomson, right? So, what is the expected observation? Now, the cathode rays, will they move in the same straight line without any deflection? First of all, answer for me for that question. Will these cathode rays move in the same path without any deflection? No. Everyone can understand that one, right? Why? Just because of having these two charged metal plates. Do you know what J.J. Thomson observed? He observed that these radiation deflected towards the positively charged metal plate, positive tip of the electric field. That's what happened, right? That's what happened. This is the first experiment conducted by J.J. Thomson, and this is giving very, very powerful, very strong idea, very firm idea about cathode rays. Students, tell me what is the conclusion. You can do it. You can tell me. What is the conclusion? Cathode rays are charged. Blank charge. What is the blank? Cathode rays are negatively charged. That's all. You know that electrons are negatively charged, right? And then can you see that the similarity? Did you catch it? Right? So he conducted the first experiment to find what is the charge, whether these particles are charged or neutral. Just imagine if these particles are neutral, then what will happen? Without any deflection, the cathode rays will go in the same straight line, in the same path. Understood? But here what happened, these cathode rays deflected towards the positively charged metal plate because they are negatively charged. That is the main conclusion from the first experiment. So we can write down what is the conclusion of this experiment, right? So conclusion from this experiment, we can say that this concludes that the cathode rays are negatively charged. Negatively charged. Try to understand. This is the first experiment conducted by J.J. Thomson to find out what is the charge for cathode rays. Do you have any doubts? Yes, we are discussing page number 8. Okay, if you have the tute, page number 8, we are discussing about, yeah, page number 8. Not the properties exactly. Yeah, these are the properties of cathode rays, but we are analyzing these things as experiments conducted by J.J. Thomson. Page number 8, after the first point, you have to draw this diagram. Page number 8, if you have the tute. Others, you just write down experiment number 1, conducted by J.J. Thomson. Draw the diagram and write down the conclusion. Okay. After you get the tutorial, you can fill these things. Don't worry, I'm uploading the note soon after the class. Okay. So they have given cathode rays are obtained as a string of invisible radiation using an anode that had a hole at the center. The cathode ray beam passing through an electric field that is between two charged plates deflect towards the positive tip of the electric. Conclusion is cathode rays are negatively charged. Yeah, same intensity. Just imagine the voltage source that we used before. Same thing. So why the gap between anode and cathode decrease? Yeah, that's a good question. Now remember, if we keep the anode here in this way, what will happen? Just imagine you are going to keep the anode here in this way, in here. Plus, some of the radiations will go for this direction as well. Then you can't get the correct observation. So that's why he decided to keep the anode a little bit front. They reduce the gap between anode and the cathode, right? So he made a hole inside the anode because we want to get these cathode rays out of the anode, and then wanted to see the deflection of these particles in the presence of this electron. Okay. So can this deflected on magnetic field? Yes. I want to remind you that, students. Now, instead of this electric field, just imagine we keep a magnetic field, right? North pole, south pole. So what do you think? Remember, students, in the experiment, actually, they have observed that in the presence of magnetic field, cathode rays are deflecting perpendicular to the magnetic field, right? Not for the direction north pole or south pole, neither north pole nor south pole. These cathode rays are deflecting towards the perpendicular direction of the magnetic field, right? So you will learn those things in physics. Magnetic fields, you're having a lesson known as magnetic field physics. So you will discuss those things in detail. Okay. So try to understand, in the presence of magnetic field, what will happen to the electrons? In the presence of magnetic field, electrons are moving perpendicular to the magnetic field direction. Yes, we can say like that. Fleming's left-hand theory. Yeah. So you can still remember the things you learn in all over time. No? That's good. Right. Students, shall we have a look in the video that we saw before again? Because in that video, they show the experiment. I put the video without sound. I'll explain that one, okay? Right. Now look at here. See, now they keep these kind of two metal plates, positive charge one and negative charge one, as you can see here. So the cathode rays are deflecting towards the positive metal plate. So you can see the deflection clearly. Can you understand? This is what happened in the cathode ray tube. If we keep this kind of a charged metal plates, that means if we create electric field. Try to understand. This is magnetic field. See, in the presence of magnetic field, what happened? So they are perpendicular. They are perpendicular to the magnetic field direction, right? Right. Please raise your hand. Those who understood the first experiment that we discussed here quickly. Please raise your hand. Good, very good. Right. Okay, then students, let's move to the second experiment quickly. Now, the second experiment is also very interesting. So, friends, we can't imagine sometimes how they thought about these things, isn't it? Right? How they get this kind of an idea, even to conduct that experiment. How did he get that idea? Right? So, don't you have that question? Experiment number 2. Let's see. This is very interesting. So, what he has done in the second experiment, he kept an object in front of the cathode. So this is the cathode, negatively charged cathode. In front of the cathode, he kept this kind of a metal cross. Okay. We know that actually Christian people actually they're using a metal cross. Okay? So that's very common. So that kind of a thing. Right? So we know that. So as usual, cathode and anode is connected to the, now anode is connected to this metal cross. So this is the anode, which is positively charged. Understood? So therefore, anyhow, these cathodes are moving towards the anode. Our metal cross is the one acting as the anode here. In this way. Right? So what he observed was, from the opposite side of the cathode ray tube, he observed the image of this metal cross with sharp edges, right? With sharp edges, with the same size, he observed the image of this metal cross, image of the metal cross, right? Let me name this one as anode, metal cross, which is connected to the anode. And this is the shadow of metal cross with sharp edges. Right. Can anyone tell me what kind of a property is explained here by J.J. Thomson of cathode rays? What kind of a properties of cathode rays, as you think? Huh? Yes, very good. Rishma, that's correct. Remember, students, J.J. Thomson proved here that cathode rays are moving in a straight line, like light. Right? That means cathode rays are actually proving here the wave properties. Light, just imagine sunlight, really. So when you go out, you know that your shadow is there. Right? So therefore, cathode rays are moving in a straight line. So if the cathode rays are moving for random directions, we don't have a shadow exactly similar to the object that we use. A shadow with sharp edges, exactly similar to that one. So the conclusion had from this experiment was what? He concluded that cathode rays cathode rays travel in a straight line, like a light, right? This explains wave nature of cathode rays or electrons. Can you remember at the content I told you that duality nature means wave nature as well as particle nature. So this experiment is clearly explaining the wave nature of the cathode rays, right? Wave nature of the cathode rays. So I'll show you another video of this experiment. So before you note down this one, please give me a second. So let's have a look on that video as well.
The anode, and it casts the shadow of the electron beam on the front of the glass tube. Now, with 5,000 volts across the cathode and anode, electrons come off the cathode, they move towards the anode but cast a shadow on the glass tube at the front, and it's the tube is lighting up under the influence of the electrons striking it. Now I can flip the anode out of the way, and what happens is we're left with a positive image on the front of the tube rather than the negative image that you can see at the moment. So here we go, we flip it down and you can see a positive image there.
Cathode rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to
Right, okay. Did you see that one? Right? The image of the metal cross is exactly can be seen on the opposite side of the cathode ray. So this is the second experiment conducted by J.J. Thomson. Right? So this is clearly explaining, try to understand this experiment is clearly explaining the wave properties of the cathode rays. Okay. Second experiment. Please raise your hand. Those who understood that second experiment clearly. Any doubts? Anything? Right. Right. Okay. Now students, let's move to the third experiment quickly. You have to draw this one. Okay. First of all, draw this one quickly. Quickly, we don't have time. Draw this one quickly. So do you use static electricity to make charge electrodes? Oh, there are any methods? Usually we are using a voltage source of the static electrodes. We are connecting that one to a voltage source. Now just imagine you have two metal rods. So when you connect that one to a voltage source, positive and negative terminals. So the one is connected to the positive terminal, that is the anode, and the other one is cathode. Commonly, that's what we are. Now you saw that in the video also, a red color clip and a black color clip was there. So they have connected to a voltage source, a battery or something like that. Right, okay. Students, are we done with this quickly? You have to write down everything quickly, note down everything. Done, right? What about the others? Done. Right. Okay. We have only 5 minutes remaining. So I want to discuss few things with you. First of all, how was the first class? Is it boring? So normally, I want to tell you that I told you last week, this is how our class is happening, right? So you can ask from your seniors, those who attend for my classes. Sometimes maybe you know that. Completely 3 hours without wasting time, we are going to discuss everything, right? So many students are telling very interesting, especially 25 and 26. Sometimes they might feel boring, but so that depend on the person. But this is my way, students. I don't have time to waste my online classes. Continuously 3 hours, we are going to work. That's the way. Okay, right. So first of all, raise your hand those who understood the things that we discussed today. Quickly raise your hand. Let me see. If you have any doubts, put your doubts in the chat box. Anything. Right. Okay. So today we discuss about the content. We started about the discussion of atomic theory, and I explained you what is the history behind that one. And then we discussed about discovery of electron. Then we came to the topic cathode ray tube, and I explained you the cathode ray tube, and we discussed about 2 experiments conducted by J.J. Thomson in this cathode ray tube. Yeah. I will upload the recording as soon as possible. Okay. Yes, students, give me a small feedback in the WhatsApp group soon after the class. So I need that one from you. I want to know what is your opinion about our class, right? So those who didn't register for the class, please give your details for the our class coordinators. Miss Sanduni and Miss Indika is there. So are there. So give your details, and from next week, yeah, next week we can do the class. I think 16th. So therefore we can do the class, no issue. So those who didn't get the tutorials, you will have the tutorial very soon. So therefore give your address details properly to get the tutorials. Okay. So that is a reminder. So we will send you the tutorials as soon as possible. Okay. And we are making a permanent theory group before the next class. So those who did the payments, and you will be added to the permanent group. So from the next week onwards, we are going to do the classes in that way, right? But you will get the tutorials if you register properly by giving addresses. Okay. Right. Okay. Anything that you want to ask? Any doubts? Anything? Okay, right. So thank you for your compliment. Okay. Yes, time going. Yeah, we can't feel even time going. Understood everything clearly. Okay, very good. So give me a feedback on the WhatsApp group. Okay, right. Okay, then only admin can message, no? But only admin can message. Yes, thank you. Thank you. Yeah, always my explanation. So if you are telling that the explanation is interesting, yeah, that is the thing. Okay. So that is actually my positive. Okay. Yeah. I'll change the settings in the WhatsApp group. Then you can give a feedback. Okay. So in the WhatsApp group. Right. Okay. Students, then let's meet on the next class. Next Wednesday, we are going to meet on the same time, 8 p.m. to 11 p.m. So next week, we are completing the discovery of discussion of discovery of electron, and we are going to discuss about the discovery of proton, right? And those things in the next class. So get ready for that one. So let's meet on the next week. Until then, bye bye. Have fun. Good night for all of you. God bless you.